Hello students, good day. I hope all of you are safe and maintaining good health. For the past three lectures, we are discussing the memory management unit where we discussed how logical addresses are mapped onto the physical addresses. In this regard, we had discussed how different processes are stored on the main memory through the contiguous allocation and non-contiguous allocation. In the contiguous allocation, we discussed fixed and dynamic partitioning, and in the non-contiguous allocation, we had discussed paging. In today's lecture, we will discuss some details related to the implementation of paging through translation look-aside buffer, and then we will discuss some optimization on this paging technique through some discussion on the structure of the page table. As we had discussed earlier, that each process is associated with a page table, and these page tables are stored on the main memory. So for each process, the page table contains the number of pages and their mapping onto the particular frames that are present onto the main memory. Usually we have a page table based register associated with a process that points to the page table, and then we have a page table length register, as we had discussed in the previous class, that indicates the size of the page table. The very same thing can be achieved through the valid invalid bit as well. So when we have this paging scheme in place, every instruction fetching requires two memory accesses. We require one memory access to access the page table, and then once we have that mapping and once we translate to get the exact physical address, then we require another access to the main memory to fetch the instruction or the data. So it means that in order to execute one instruction, we require at least two trips to the main memory. One trip to get to the page table and to get this translation of the page number to the frame number. And then the other trip is to fetch the actual instruction or data. So these two trips, they cost a lot in terms of speed and time. So these two memory access problem can be solved through a translation look aside buffer, and we will look into the details of it onto the coming slides. Over here we have the paging scheme. So once a CPU generates a logical address, we divide it into two components. The first one is the page number, while the other is the page offset. This page number is searched from this page table and gets translated into a particular frame number. And this frame number is again attached with the page offset to generate the exact address onto the physical memory. So this is the usual implementation of the page table, where we require two access to the main memory in order to fetch one instruction. However, through this translation look aside buffer, we add an associative memory over here to make sure that once we access to some page number, we fetch it and store it in this associative memory. Now, this memory is a bit faster and provides faster access, so that next time when the same page number arrives at this logical address, we can search it from this associative memory, and we may not have to take a trip to the main memory for this page table. Again, as we have in the usual scheme of paging, in the associative memory, we again have page number and its corresponding frame number. Once it is stored in the associative memory, next time once we have to get a particular logical address translated into the physical address, we look it from the associative memory instead of going to the main memory for this page table. So we have once we have this TLB, we may have a particular address present in this TLB, or we may not have a desired address present in this TLB. In the first case, when we have the address stored in this associative memory, we will call it a TLB hit. In other cases, when the page number is not present on this TLB, we will call it as a TLB miss. Once we have a TLB miss, means that the page and the frame number is not present on this associative memory, then we again have to take a trip to the main memory in order to fetch the desired page number to frame number translation. So over here we have the implementation of paging through this TLB. So you can see that the rest of this mechanism remains the same. And over here we have an addition of this associative memory in the form of TLB. So this TLB again has this translation that we have on the page table. However, it has only some records out of the main page table, and that is why it is a lot faster compared to the access to the main memory to fetch the page number to the frame number translation. So usually once we have this logical address generated, and we have to look from the page table for a particular frame number, instead of going to the page table, first of all we look for the desired translation into this TLB. If we have a TLB hit, we move to this logical address construction, and we create it by putting the frame number as well as the page offset that we get from the logical address as such. Once we have this complete physical address, we go and hit the physical memory in order to fetch the desired instruction. However, in the case when we do not have the desired translation present on this TLB, we call it a TLB miss. And in this case, we have to go to the page table that is present in the main memory in order to fetch the desired translation, and then we generate this physical address by putting in the frame number and taking the offset part of the logical address, and we get this physical address and the data from the physical memory. Now you can see that if we have some advantage over here in the form of TLB, for instance, if a trip to this page table requires 10 seconds and we have this TLB access in 1 second, so you can see that in the usual operation, when we do not have this TLB, 2 trips to the main memory will take 20 seconds, 10 for the page table and 10 for the extraction of the actual instruction. However, in the presence of this TLB, and if the access time is 1 second, then you can see that this translation can be done in 1 second, and then the actual fetching of the instruction can again happen in 10 seconds, and then we will get 11 seconds total access time to fetch a particular instruction from the main memory. So you can realize that this is really a positive improvement on this time that we spent during this translation. However, at the same time, when we have a TLB miss, it means that first of all we will look into this TLB for 1 second, then we have to go to the page table and take a trip in 10 seconds. Once we get this translation and populate the fields to generate this physical address, then an actual trip to the main memory to fetch the desired instruction will take another 10 seconds. It means that in a case of TLB miss, we have to take 1 second, 10 seconds, and 10 seconds means 21 seconds. An additional overhead of 1 second that we have to face if the number is not present on this TLB. So now we have both of these cases. In the form of TLB hit, we will get additional advantage, and in the case of TLB miss, we have some drawbacks, or we have some a lapse of time or wastage of time in this regard. So, in the presence of both of these hit and miss scenarios, we should find some effective time for this TLB hit and TLB miss to find out an average time to fetch a particular instruction from the main memory in the presence of this TLB. So on to the coming slide, we will get this effective access time through the calculations and through the hit ratio that we have on a particular TLB. Now let's calculate this effective access time in the presence of a TLB. So let's suppose a hit ratio is a percentage that presents the number of times a page number to frame number translation can be found onto the TLB, while the miss ratio is the number of times when we are unable to find this page number to frame number translation, and this can be achieved through 1 minus this hit ratio to get that miss ratio. So the number of times we are unable to hit the TLB, we have a miss. So now let's consider the timings for this TLB search. So for a TLB search, we have an effective time of 20 nanoseconds. So in 20 nanoseconds, we are able to assess a TLB translation. On the other hand, if we have to get it from the main memory, we may require 100 nanoseconds for this operation. So for a TLB hit, we have one trip to the TLB and then one trip to the main memory to fetch the actual instructions, which means we have 120 nanoseconds for a TLB hit. On the other hand, if we have a TLB miss, which means that we have to take a trip to the TLB, then one trip to the main memory to fetch the translation from the page table, and then one trip to the main memory to fetch the actual instruction, which means that around 220 nanoseconds are required in the case of one TLB miss. So now we have a time when we have a hit in the TLB, and then we have a time when we have a miss in the TLB. Now we will calculate the effective access time when we have a particular hit ratio. So let's consider a quite moderate hit ratio, that is 80%. This is a bit modest estimation because in reality it is closer to 95%. So let's suppose that we have a 80% hit ratio. So we will multiply this 0.8 into 120, the effective access time for a TLB hit. So we will get around 96 nanoseconds, and then we have a 0.2 into 220, and we will get around 44 nanoseconds in this case. So a total of 140 nanoseconds is the effective access time when we have a hit ratio of 80%. On the other hand, if we take a bit more realistic hit ratio, that is around 98%, so we will multiply this 0.98 with 120. So we will get somewhat 118, closer to that. And then we have the remaining 0.02 multiplied by the time that we get in the case of a TLB miss, and we will get around 4 in this case. So a total of 122 nanoseconds is the effective access time in the case of a hit ratio of 98%. So you can see that it is quite closer to 120. That is the ideal case when we have 100% TLB hit. So this is not a lot of compromise on the effective access time when we have a good hit ratio in the TLB. when we are implementing the page table, we have to face several challenges in terms of memory access as well as the space required to store one page table in the main memory. So to address these challenges, we optimize the structure of the page table, and in this we will discuss the hierarchical page tables, hashed page tables, and inverted page tables. So let's discuss the general structure of the page table before we move on. So we know that in a 32-bit architecture, we have 32 bits logical address space. So if we take a page size that is of 4 kilobyte, which means 2 raised to the power 12, it means that out of the remaining entries, we may have 1 million entries in the page table. So if one entry takes 4 bytes, the total space that is required to save one page table is closer to 4 megabytes of memory on the main memory, on the RAM. So this memory is required to store one page table associated with a particular process. And if we look in terms of the usage of the main memory and the operating system, then this is a lot of memory that we are wasting just to support the concept of paging. And even if we do not want to allocate this in a contiguous fashion onto the main memory, then there is again another issue of how to find out the pages and frames associated with this page table. To address this issue, we can use hierarchical page tables where we split up the logical address space into multiple page tables instead of one. You can consider an analogy where you have to point to 8 records in a table. So to point out to those 8 records, you may require 3 bits, starting from 000 and going till 111. So now in order to access a record or to search a record from all of these, you may have to traverse the whole list. 8 possibilities are there. So if you just divide it into 2 layers, one having 1 bit while the other having 2 bits. So for the 1 bit you may have only 2 options, 0 or 1, and for the other 2 bits you have 4 options starting from 00 and going till 11. So all in all, you now require 6 traversals or 6 comparisons rather than 8. And if you just extend this concept to have like 4 bits, and you can access probably up to 16 records. So if you just take it in one layer, you may require 16 comparisons. However, if you just divide it into 2 layers, you may require 4 comparisons for the first 2 bits and 4 comparisons for the next 2 bits, which means 8 comparisons in total. So the very same analogy can be handled over here or applied over here on page tables, where we split up the one page table into multiple page tables to ensure that we are not required to have 1 million page entries, and we are not required to traverse all the list in order to find our desired page. So a simple technique is a 2-level page table where we just split up 1 million entries into 1 kilo and 4 kilobytes entries, which means that 1000 and 4000 entries to solve the whole thing. So over here we have that concept in working. So on top we have an outer page table, and then we have an inner page table, and then we have actual pages stored onto our main memory. So outer page table will get us to the first couple of bits, and then the inner page table will give us the other bits that are relative to the page table bits, and then we will get the offset, and then we will end up in the main memory for the particular page that we are looking for. Now let's consider the same example with a 32-bit architecture. However, this time instead of having 12 bits and having 4 kilobytes page size, this time we have 10 bits and 1 kilobyte page size, and the page number is divided into these 22 bits. So you can see that this time we have 4 million entries in this page table. However, if we divide it into two layers, the first having 10 bits and the other having 12 bits, this 10 bits will reflect 1000 entries, while these 12 bits will point to 4000 entries, which means that instead of having 4 million entries in the page table, now we can achieve the very same results using only 5000 comparisons. So you can see that the lookup for page table will be enhanced efficiently by using this two-layer paging example. The example that we had on the previous slide refers to Pentium 2 machines that we used like a couple of decades earlier. So over here we have that particular concept in practice. So now our logical address is divided into three components. The first component refers to the outer page table. The second component refers to the inner page table, and then we have the offset that is added to the after the translation of the page number to the frame number, and then we can find the particular page that is present onto the main memory. This scheme may work fine for 32-bit architecture. However, when we move on to 64-bit logical address space, even this two-level paging is not sufficient. Let's consider an example where we have a page size of 4 kilobytes in a 64-bit logical address space. So this will leave around 52 bits out of the 64 bits. So our page table has 2 raised to the power 52 entries. If we deploy a two-level paging scheme, still the outer page table will get 42 bits and 2 raised to the power 42 entries will be stored in there. So you can see that even this is not feasible for a system where we have 4000 million entries in the outer page table. One possible solution to address this issue is to add another layer on top of our outer page as the second outer page table. However, in this case, our second outer page table will still get 32 bits and a total of 2 raised to the power 32 entries, which means around 4 million entries. So you can see that even after having this much compromise on the number of entries that are present in the second outer page, we still may require 4 memory access to get to one particular memory location. So you can see that we have second outer page, then we have outer page, then we have inner page translation, and at the end we will get this offset, and we will get a complete address on the memory for a particular instruction. So you can see, even though it is not very feasible with respect to the number of elements present, however, still we require 4 memory access, which means that the speed of the system will compromise a lot. To get the very same level of page tables or the length of the page table in thousands, we may require 7 levels of paging, and which require again 7 memory access to get to one memory location, which means that this is not going to work for 64-bit logical address space. As we have seen that hierarchical page tables cause a problem of tremendous searching, as there are a lot of elements present in the page table when we have an address space greater than 32 bits. So for such address spaces, we have the solution in the terms of hashed page tables. In this method, we pass on the actual page number to a hash function which generates a virtual page number, and then we store that virtual page number onto the page table and against that virtual page number we have the frame number. So now we have the actual page number, that which is hashed to generate a virtual page number, and now this virtual page number is stored onto the page table to get translated into an actual frame number that is present onto the main memory. Now the range of this hash function is usually smaller compared to the actual page number domain. You can take an example. If you have 100 elements and you want to find a number from those 100 elements, you may have to perform 100 comparisons for this purpose, which is definitely difficult. So you can use a hash function of 10, so of range 10, where the maximum possible value is from 0 to 9. So in this case, if you pass any of those 100 values to that hash function, it will produce a number that is from 0 to 9. So that definitely there will be 10 times less number now present onto this hashed range. However, we also encounter a problem when we have this, because we are trying to compress the range, multiple values from the original domain from 1 to 100, they will fall onto the same value of this range. So it is possible that number 87 and 77 both fall onto a virtual value of 7 or a hashed value of 7, which may cause a collision. So to handle this collision, we may use a linked list so that multiple entries can be stored against 7. So we know that the hash value is 7, and then against 7 we can search our desired element through a linked list. Even though we have to traverse the linked list, but the number of comparisons will be a lot less than compared to the actual case when we have to search it from 100 elements. So we are trying to do the very same thing over here with the page table. So we have like a million entries in the page table. We hash them to generate like 1,000 entries, and now against any virtual entry in the page table, we have a linked list of values that can fall against that actual page number. And once we get that actual value from the page table, we get it translated through the corresponding frame number, and we get to the main memory to fetch the actual instruction. So in this way, we reduce the number of entries that are present on a page table. So usually each element has a virtual page number, and against that virtual page number we have a mapped frame number that is present onto the main memory, and then we have a pointer to the next element for maintaining the linked list. So this is how we generate a virtual page table or a page table of virtual values of the actual page numbers. Now comparisons are done in this page table having virtual values, and once we find our desired virtual page number, we get to its chain and we try to find out the actual entry where we have the translated frame number, and we take the corresponding frame number and we get to the physical memory to extract the instruction that is stored in there. So over here we have the concept of hashed page table in working. So you can see that against a page number, actual page number, we pass it to a hash function that generates a virtual page number, and that virtual page number is stored in the page table against the frame number. So now you can see that multiple entries in this actual page numbers will end up on the same virtual page number. So we will have multiple frames against those actual entries. So we keep a linked list having multiple entries, and once a particular page number ended up against a particular virtual page number, we traverse this linked list to fetch the actual map, and then we translate this frame number against this page number to get to the uh, generation of the physical address that we have placed in here. And once we have this physical address, we can get to the main memory and fetch or decide instruction. So you can see that instead of having multiple layers where we have to access the main memory multiple times, just by adding a couple of computations, we can generate we can get to the memory just in a couple of memory access. So the problem of massive searching is solved through hashed page table. The next issue that we face in paging is the space requirement. Usually we have one process associated with one page table, and each page table is stored in the main memory. It means that if we have n processes running in a system, we have n page tables stored in the main memory. And because the size of the main memory is limited, so it is also possible that not all of the pages associated with a process they are stored in the main memory. So even if the pages are not stored in the main memory and we do not have any frame translation for each page associated with a process, still we may require to store that entry in the page table. So to address this issue, we have inverted page tables where instead of storing page to frame translation, we look for the presence of actual pages that are present in the main memory. And against those actual pages, we have those frames associated, and we have a valid invalid bit to identify which of the pages are present onto the main memory. And for this each entry for pages onto those frames that are present onto the main memory, we have a page table. So now instead of having a page table for process page to memory frame, we have an inverted page table that has actual memory frame associated with the page of a process that is present in the main memory. And to address this in terms of multiple processes, we have process ID associated with it as well. So now the inverted page table has process ID, page number, and the actual frame number where this page is present onto the main memory. So in this way, now we are not required to have independent page tables associated with each process. Rather, we have an inverted page table that is associated with the whole main memory, and we reversely map it to the processes pages that are present onto the main memory. This solves the problem of the excessive memory that is required to store independent page tables associated with different processes. However, at the same time, it increases the time that is required to search the inverted page table, because now along with the page number to frame number translation, we have to find the reference of the particular process as well. However, to limit the number of searches in this inverted page table, we can use hashed page tables to reduce the number of searches. Also, we can use the translation look-aside buffer to speed up the process of accessing the memory. So over here we have a conceptual view of this inverted page table. So you can see that we have a page table where we have this mapping of process ID and page number, and we have a particular frame that is associated with these entries. And along with this pair, process ID and the page number, we get that particular frame that is present onto the main memory. So the offset remains the same, and we get the physical address where this particular page is actually located onto the main memory. All right, in today's lecture, we discussed various implementation details of this paging technique. And in this regard, we discussed the translation look-aside buffer, and we calculated its effective access time in the presence of a particular hit ratio. Moreover, we discussed the structure of the page table and various challenges that are associated with it. So that is all for today, students. Please take good care of yourselves. Thank you.